Okay. Sorry about that. Okay, 2.1 and 2.2. Okay, 2.1 is the natural exponential and logarithmic functions. Okay, a little bit different than the exponential and logarithmic functions that we've been talking about so far. This is the one that's called the natural, if I can spell it correctly. The natural exponential and logarithmic functions. So the emphasis is on the natural here. Okay, so where does this come from? Well, let's look at, let's consider compounding interest here. Okay, consider the compound interest formula. Okay, A is equal to P times 1 plus R over N to the NT. So there's our compound interest formula. Okay, where N is the number of compounding periods. Okay. Okay, so let's look at a special case of this. Let R equal 100%. Okay, and my principal P equals $1, and T is equal to 1 year. Then A, okay, would become this. It would become $1 times 1 plus 1 over N to the N times 1, okay, which is going to simplify to 1 plus 1 over N to the N power. Okay. Now, this would be equivalent to saying that I'm going to compound $1 at 100% interest for 1 year. Okay, so basically I'm going to double, right? If I only had one compounding interval here, I would just go from 1 to 2. Okay, I'd start with $1. $1 would become $2 if N is equal to 1. Okay, but well, let's do it backwards here. If I plug in N is equal to 1, then that just means that I will have doubled my money. Why doubling my money? Because I will have increased my amount by 100%, right? That's what that 1 up top here means, right here. This 1 here means that I'm increasing by 100% for the year. Oh, okay. So the simple interest here would just be I'm doing 1. Okay, if N is equal to 1, then it goes 1 plus 1 over 1 to the 1 power, which is equal to 2. So I went from $1 to $2. Okay, so, or sorry, the N is the number of compounding intervals, but I would have started with, again, P is always equal to $1. So P is equal to $1. So I went from $1 to $2. Now, let's see what happens when we compound. Okay, can we make more money? Can we get this to be more money? And we can actually. If we take that $1 on the outside and we go 1 plus 1 over 2, now to the second power, this becomes 1.5, okay, but I'm compounding it twice. Okay, it's 1.5 compounded biannually. And so this ends up being $2.25. So I made an extra quarter by compounding. Okay, so what would happen if I did it monthly? Okay, what would that come out? Would I make even more money? And the answer is yes, I would. Let's see what happens here. We're going to go 1 plus 1 divided by 12. And I'm going to take that value and I'm going to raise it to the 12th power. Raise this to the 12th power. And I get 2.61, $2.61. So I turned my dollar into now $2.61 by doing it monthly, 2.61. Okay, and it would behoove us to want to compound as much as possible, right? Like if we could compound this, you know, 365 times in the year, like one every day, then we would make even more money at the very end. We get $1. This is not right. Is it froze? Don't freeze on me. Oh. Technology, I love it. Yep, it froze. Sorry about that. Okay, let me reboot my computer. Technical difficulties. Go. Come on, go back. There we go. Okay, good. Okay, so if we did this, invested our $1 and compounded now 365 times a year, what would we get then? Let's go back to our calculator. Okay, actually I need the scientific one. There we go. Okay, and oh, we got 2 of them up there. Let's get rid of that one. Okay, so let me bring it over here actually. Okay, so we're going to say 1 plus 1 divided by 365. And we're going to raise that, it's nearly 1. Okay, the fraction is really small, but we're going to raise that now to the 365th power. Okay, and I get about 2.71. Where'd the calculator go? 2.71 or $2.71. Okay, now what we really want to do is take this thing and we want it to compound infinitely, like every millisecond. Okay, because if we can compound this infinitely, then we get the maximum amount of money that we can get within that year's period. Okay, I will have taken that $1 and I will have maximized the interest output for that $1. And the idea is that we want to take the limit, now that we know what a limit is, limit as n goes to infinity of 1 plus 1 over n to the nth power. And when I take the limit of this, okay, this ends up being, through computation, 2.718281828 45 90 45, and then it just goes on forever. Okay, and so this is what we call the natural base. We call that base E. Okay, this is base E, or the natural base. Okay, and so on a calculator, there's generally, on a scientific calculator, there's the EXP or the EP. Okay, I don't know, this has the E key, and you can see when I press on the E key there, it has 2.718281828 45 90 45, which is what I wrote out here. Okay, and that's the E, that's the natural base. Okay, so now let's consider what happens as we compound continuously. Let's go back to our compound interest formula. So we're gonna now generalize this. We're gonna say, well, what's the general form when before we found E, when it was $1 invested at 100% over 1 year, but can we generalize this compounding continuously thing for any principal at any interest rate over any time? And that's what we want to do now. So let's go back to our regular compound interest formula. This is 1 over n, 1 plus r over n to the nt power, right? Okay. Okay, so I'm going to do a little substitution here. I'm going to say that m is equal to n over r. Okay, m is equal to n over r. And so what that's going to allow me to do is rewrite this equation up top by letting the m be kind of this dummy variable. Okay, it's going to replace this n over r. Well, how would I rewrite this r over n in terms of m? Well, if m is equal to n over r, then 1 over m is equal to r over n. Okay. Okay, so it's just the reciprocal, right? It would be like flipping it upside down. So I'm going to say, oh, okay. So A is equal to P times 1 plus 1 over M. Okay, 1 over M to the what? To the NT power, but I want to get this in terms of M and not N. I'd like to substitute out, we want to sub out M for N. I don't want to have any N's, I just want to have M's. Okay, and there's a reason that we're going to do this, and it will turn out really nicely in the end. Okay, so what is N equal to? Well, N is equal to, if I multiply both sides of this equation by R, then N is equal to Rm, or MR, I should say. Okay, either way. Okay. So what is this going to become? Well, this is going to become MRT, or Mr. T. I'm just kidding. Okay, it's MRT. Okay, it's this M, this dummy variable M, times the rate times the time. Oh, okay. This guy as P times 1 plus 1 over M to the M power, all raised to the RT power. Because a power to a power is just, you just multiply. If I had A to the B times C, that's the same as A to the B to the C. Okay, it's just when you have a power to a power, you just multiply the exponents together. So what is this? What happens as what happens with the limit of this as m goes to infinity? As this compounding increment goes to infinity, this whole thing, okay, 1 plus 1 over m to the m power goes to e, base e, that 2.718. So this whole thing, okay, get rid of that. This whole thing here goes to e. Oh, okay. So this just becomes a equals p e to the RT. And this is called my continuously compounding interest formula. It's a equals p e to the RT. It's also called a PERT account, PERT. Okay, and that's when you have continuously compounding interest. Okay, for any principal, rate, and time, you can plug it into this formula using that 2.718 as your base, right? So this is approximately 2.718, okay, as your base, and you can get the continuously compounding interest formula that's going to give me the value of maximum return on my investment, okay, if I continually compound. Okay, so we say that the natural exponential function, okay, is f of x is equal to a e to the x. Okay, this is the natural exponential function. Okay, so in this case, x is behaving like RT and a is behaving like p. Okay, but we say that is the natural exponential function. We're going to see why we study this, because there's some nice properties about this. Okay. The natural logarithm okay, is the inverse of the natural exponential function. Y equals e to the x. Okay, so the natural logarithm is the inverse of the natural exponential function. Okay, so if we switch the x and the y, which is how we get an inverse, if we swap x and y, which produces an inverse, that's how we get an inverse equation, the opposite equation. Okay, then we can say that x is equal to e to the y. And now I want to solve for y. I want to solve for y here. I swapped the x and the y in my natural exponential equation. Okay, this is a swap of x and y in the natural exponential equation. Okay, and I want to write this in terms of a log. Okay, so how would I write this in terms of a log? Well, I would say that y is equal to log base e of x. Okay, and so these two equations, y equals log base e of x and y equals e to the x, these are inverse operations. They are opposite operations. The natural logarithmic function, which is this, okay, and the natural base are opposites. Okay, they are opposite operations. One undoes the other. It's like adding 3 and subtracting 3. Those are opposite operations. One undoes the other. Okay, now the way that we write log base e is ln, or the natural log. We call this the natural log ln. Okay, so It's just an abbreviation for log base E. Okay, and it is called ln is natural log for short. Okay, so we always like to shorten things in mathematics, abbreviate them if we can. And so we just say this is the natural log, okay, or ln, okay, log base E. Okay, let's take an example here. Let's solve an equation using natural log. So let's solve 2 plus 3 natural log of x minus 1 is equal to 8. Okay. So how can I solve for x? Okay, well, the first thing I'm going to do is subtract off the 2. I'm going to get 3 times natural log of x minus 1 is equal to 6. Okay. Now let's divide by the 3. I get natural log of x minus 1 is equal to 2. Okay. So now I want to write this in exponential form. Remember, what is natural log? Well, natural log is log base E of x minus 1. So what would this be in terms of an exponential form? It would be x minus 1. Remember, what are we asking with the log? With the log, we're asking e to the what power is x minus 1. E to the what power is x minus 1. Yep. And it's e to the second power. What's the question that's being answered. Okay, e to the second power. Oh, okay. So this becomes x minus 1. I don't even need the parentheses anymore. Get rid of those. And so I'm going to add 1, and x is equal to e squared plus 1. If I were to plug that into a calculator, okay, e squared plus 1, okay, is that right? Nope, not right. Let's do e squared plus 1. There we go. It is about 8.39, I would say. Okay, about 8.39. That's a 3. Okay, let's see how this works in investment and credit. Okay, number 2, Marissa invests $12,000 in an account that earns 2.8% interest, compounded continually. Okay, when will her account double? Okay, when will her account double? Okay, so we're compounding continually. Well, that's a PERT account. That's my A equals P e to the RT, right? Okay. And so we're saying, look, she's going to invest $12,000. Okay, so A equals $12,000 E at 2.8%. That's 0.028 times T. Okay. But we need to solve for T. They don't give us A. What is A? What should A be?
The final amount.
Yeah. What should the final amount be? It should be double, right? So yeah, very good. Thank you, Giselle. It should be 24,000, right? Isn't that double? Okay, so now let's divide by 12,000, and we get what? We get 2. 2 is equal to e to the 0.028 times t. Okay, so now I want to solve this for t. Well, I can put this in logarithmic form if I want to and be able to solve for t. Or I could say, hey, you know what? I know that when I take the natural log of e to the x, that's just x. Why? Why is that just x? Because what does natural log stand for? Natural log stands for log base e of e to the x is equal to x. And is that true? Is the natural log of e to the x x? Well, what does this ask me? This asks me the log base e of what power is e to the x power? Well, wouldn't that just be x? E to the x power is e to the x? Yeah. So that just equals x. Basically, these two functions, the natural log and the exponential, cancel each other out. Why? Because they're inverses. That's how we designed them. We designed them to cancel each other out. Oh, okay. So I could take the natural log of both sides here. And I'm going to end up with the natural log of 2 is equal to 0.028 times t. Now, again, if you don't like that, you could do it the old-fashioned way. You could say, oh, okay, 2 is equal to e to the 0.028t, right? But we could say, oh, well, this is log base e of 2 is equal to 0.028t. But what is log base e? Isn't that just natural log? I mean, either way, we get to the same spot. Okay, this is, I'll call this method 1. Okay, and I'll call this method number 2. That's a really sloppy writing. Okay, method number 2. Okay, so this would be natural log of 2 is equal to 0.028t. Either way, we get to the same spot, right? Okay, so now let's solve this. Let's solve this. Well, I'm just going to divide by 0.028, and we get t is equal to the natural log of 2 over 0.028. Oh, okay. Okay, and so t is really equal to, I'm going to write it a little bit more like this. I'm going to say, hey, you know what? This is going to be natural log of 2 over the rate r, right? Isn't that really essentially what we did there? Was we took the natural log of 2 and divided by the rate? Okay, remember when we talked about the rule of 72? This is essentially what we're doing here. We're saying the rule of 72, which should really be called the rule of natural log 2, but since natural log 2 is approximately 0.693, it's pretty close to 72, and since 72 has a lot more factors than 0.693, we just call it the rule of 72 and not the rule of natural log of 2, which is really what it should be called. We're just going to take that natural log 2, divide by 0.028. Okay, and let's see what we get on our calculator. Let's say, okay, so I'm going to take 2, and then I'm going to hit the natural log key here, natural log, and then I'm going to divide that by 0.028. Boom. And it's about 24 years, which makes sense. If you think about the rule of 72, right? You think of the rule of 72, well, 72 divided by 3 is 24. So it comes out to about, 3.28 is pretty close to 3. 0.69 is pretty close to 72. So it's not too far off. This is 24.76, I would say, or 24.8 years. Okay, So this estimate was close, not exact. We want the exact time, we have to do this. This is, okay, and what we call this formula is we call this formula the doubling time. Okay, the amount of time it's going to take for you to double something under exponential growth is natural log 2 over r. Okay, that's your doubling time. Okay, let's do another one of these. Membership on Instagram doubles every 6 months. What is the exponential growth rate of Instagram as a percentage? What is the exponential growth rate of Instagram as a percentage? Okay, well, what's the doubling time? The doubling time is equal to, okay, the natural log of 2 over the rate. Okay. Okay, so we have to ask ourselves, do we want the rate per month, or do we want the rate per year? Okay, so do we want our monthly rate or do we want our annual rate? I'm going to go with an annual rate on this one. Okay, so this is going to, it doubles every 6 months. Okay, so you think it's be somewhere around maybe, you know, we'll see what happens. Okay, if it doubles every 6 months, what is the rate of percentage? So okay, so what would be the doubling time here? The doubling time would be 0.5 or half a year, right? 6 months is half a year. Okay, this is the time. Half a year is equal to natural log of 2 over r. Okay. So I could cross multiply this. And I would get 0.5r is equal to the natural log of 2. Okay, I could divide by 0.5. And I would get my rate to be approximately, let's clear this. Let's do 2 natural log, that's a natural log of 2. And then I'm going to divide that by 0.5. And it's 139%, 1.39. So this would be a rate of 139% per year. Okay, it means that it's doubling, it's going up very fast. Okay. Okay. Let's move into 2.2 now.
Professor, I have a question.
Yeah.
If we were to do it in per month, you would just have to do it t equals to 6.
Yes. Exactly.
And then so the rate would be per month, right?
Yes.
Okay, thank you.
That would be a monthly rate. Well, that's called a nominal rate. And to get your nominal rate to your annual percentage rate, that's not multiplying by 12. It's actually raising that rate 1 plus that rate to the 12th power. to convert them. So just keep that in mind. It's not a straight conversion. Because you're like, I got the monthly rate, but it's not 1/12 the annual rate. Well, it's because you're talking about compound interest here.
Yeah, because it keeps getting compounded after every 6 months, right? Yeah.
Exactly. Okay, so let's move into the calculus part of this. Okay, that's more the kind of arithmetic part of it. Okay, so let's talk about derivatives. 2.2, derivatives of exponential functions. Okay, so what's nice about exponential functions is that it is its own derivative. That's kind of cool. Okay, it's a very, very special, let me just say here, a really nice property of e to the x is that it is its own derivative. Okay, it is its own derivative. Okay, so if I have f of x, which equals e to the x, and I take f prime of x, that's also e to the x. It is its own derivative. It's kind of interesting. E to the x, the graph looks like this. Okay, and so at any point on this graph, the slope of the tangent line is the value. That's kind of interesting. So if I take e to the 0, the slope of the tangent line is the value of the function at that point. So the slope and the y value and the slope are exactly the same. So the y value is 1 here when x is 0, right? X is 0. So the y value is 1, but also the slope of the tangent line is 1. Okay, so m equals 1. At say 1, let's go to 2 actually. Okay. 1, 2. Let's go to 2. If x is 2, then the height here is e squared, but that's also the slope. So what is e squared? E squared was about 7 point something. Okay, so e squared is 7.39, I'll say, 7.39. So that's the height. So this is 7.39. That's the height of that point. Okay, this point was at 1. Okay, but it's also the slope of the tangent line is also 7.39. So it's a really nice mathematical function in that every point on the curve, the tangent line has the slope of the value of the curve. The value of the curve and the derivative are exactly the same thing for every point on that curve. It's a very nice function. Okay. Okay, number 1. Okay, let's differentiate. Okay, A. y equals 3 e to the x. Well, what's the derivative of y equals 3 e to the x? Well, it is just 3 e to the x. It is its own derivative. Okay, even if there's a number in front. Okay, from the properties of derivatives here. Okay, what about b? Okay, b, y equals x squared e to the x. Okay, y is equal to x squared e to the x. Here we're going to want to use the product rule. Okay, so y prime is derivative of the first, 2x times the second, e to the x, plus the first times the derivative of the second. But what is the derivative of e to the x? It's itself, e to the x. I could factor out what they have in common here. They have an x in common and an e to the x in common. And so what's left over in the first one is just 2. And what's left over in the second one is just x. So y prime is equal to x times e to the x times 2 plus x. Let's look at c here, 1c. Okay, y equals e to the x over x cubed. Okay, so now this is going to be a quotient rule. Okay, so y prime, derivative of the top, that's itself, times the bottom, minus derivative of the bottom, 3x squared, times the top, itself, e to the x, okay, all over the bottom squared. Okay. So now let's clean this up. Let's simplify this. Okay, I could factor out an e to the x and an x squared. So e to the x times x squared times, there's an x left over in the first one, and there's a 3 left over in the second one. This is x minus 3. All over x to the 6th. Okay. Well, 2 of these guys, these x squareds, are going to cancel with 2 of these down here, and that's going to leave me with an x to the 4th. So this gets simplified to e to the x times x minus 3 all over x to the 4th power. And that is what y prime is. Okay. Okay, let's use the chain rule now. We've done the power rule and we've done the product rule. We've done the quotient rule. Let's do the chain rule now. Okay, so what does the chain rule look like with e to the x? Okay, well, the derivative of e to the u of x is equal to, okay, e to the u of x times u prime of x, okay, or written more simply, it's really u prime e to the u, okay? It's just u prime, whatever u was, I just take the derivative of it and I put it in front of the original function, okay? I'll put the x's here. Okay, just take the derivative of the exponent and put it in front of the function, and there you go. Okay. Okay, so let's use that in number 2 here, 2a. Okay, y equals e to the 8x. Okay, so what would be the derivative of this? Y prime. Well, what's the derivative of 8x? Well, the derivative of 8x is 8. So it just goes in front. 8e to the 8x. Okay, whatever the exponent's derivative is, that's what goes in front. Okay. Okay, 2b or not to be. Okay, y equals e to the negative x squared plus 4x minus 7. That's all the exponent. So what does this become? This becomes y prime is equal to the original times the derivative But what's the derivative of the exponent? The derivative of the exponent is negative 2x plus 4 times the original function, negative x squared plus 4x plus minus 7. And that's it. Okay, I could factor out a negative 2 if I wanted to. I don't have to, but I could. I get x minus 2 times either negative x squared plus 4x minus 7. Okay, and C, excuse me. Okay, C, y equals e to the radical x squared minus 3. Okay, let's see what happens here. It's going to be, the derivative is going to be the original e to the radical x squared minus 3 times the derivative of the power. Okay, times what's the derivative of the power here? Well, that in itself is its own chain rule. The derivative, oops, sorry. The derivative of radical x squared minus 3, let's see what the derivative of that thing is. Let's say that u of x is equal to radical x squared minus 3. Just put a question mark there. It's times what? Okay, we want to find what's u prime of x. Well, this is going to be 1 over 2 radical x squared minus 3 times the derivative of the inside, which is 2x. Those 2's are going to cancel. And so I'm left with x over the square root of x squared minus 3. Okay, so y prime is equal to x over the square root of x squared minus 3 times e to the radical x squared minus 3. That's the derivative. Okay. Let's do a couple more derivatives here. Okay, number 3 here. Okay, given n of t is equal to 80 minus 70 e to the negative 0.13 t. Okay, find n prime of t and n double prime of t. We want to find the first derivative and the second derivative of this thing. Okay, let's see what we got here. N prime of t, what's the derivative of 80? Well, that's 0. Minus 70 times e to the negative 0.13 t, e to the negative 0.13 t. That's going to be the derivative, it's going to be itself, times the derivative of the exponent. Well, the derivative of the exponent is negative 0.13. Okay, so this thing will clean up and simplify to a negative times a negative, which is positive. 70 times 0.13, let's see what that is. 70 times 0.13, that's 9.1. So this is positive 9.1 e to the negative 0.13 t. That's n prime of t. Okay, that's kind of cool. Okay, so let's find out what is n double prime of t. That's the derivative of the derivative. Well, this is just going to be 9.1 e to the negative 0.13 t times the derivative of the derivative of the function is itself times the derivative of the exponent, which is again negative 0.13. Once again, that is negative 0.13. Okay, so what's 9.1 times 0.13? That's 1.183 e to the negative 0.13 t. Okay. for a question. Is it negative? Yes, thank you. It is negative. Did I write that in my notes wrong? No, I have it negative in my notes. Thank you. It is negative. Okay, there was one other thing that I wanted to show you guys. Okay, T, solving for, we did our doubling time, that's fine. We did our compounded interest. Oh, decay. Okay, yeah. Okay, but we don't talk about that yet until 2.5, or sorry, 2.5. The doubling growth is we've already covered that. Yeah, okay. It's 2.3. Oh, derivatives of natural logs. Okay, let's keep going here. Okay. Or not. Maybe we won't. What do we got going on Thursday? Thursday is 2.3, 2.4. What's 2.0? 2.4 is, yeah. Okay, 2.3, 2.4. Okay, well, a couple of short lectures this week. Okay, so we're gonna stop there for today. Okay, that's about it. That's all you need. Okay, so that's 2.1 and 2.2. Make sure that you're working on the homework. Okay, if you have any questions on the homework, make sure you let me know or come to tutoring. Okay. Also office hours on Thursday. Okay, see you guys on Thursday. Bye.
Professor, hello, Professor Hellman.